Okay, yeah, I think we can start. So welcome everybody to today's Motivic geometry seminar. So our speaker today is Grigory Garkusha, and he will speak on semilocal Milnor K-theory.
Okay, vielen Dank indeed, Marcos. And before starting, I'd like to thank Polarna for organizing such a wonderful special year at the Center for Advanced Studies, and I appreciate virtual hospitality. And also many thanks to Glenn for administrating this seminar. Today, I'd like to speak about the so-called semilocal Milne K-theory. My primary goal was to compute, first of all, the Motivic complex of weight 2, Z2. I recall that Motivic complexes are labeled with non-negative integers, and the Motivic complex of weight 0 is very simple. It is concentrated in a single degree homologically, and it is the constant sheaf. Next, followed by the Motivic complex Z1, which is also homologically before sharing the screen, let me say a few words. I received a couple of messages with the charts. Next, Motivic complex of weights 1 is also concentrated in a single degree, and namely in degree +1, and it is the sheaf of invertible functions. This is a result of Suslin and Voevodsky, and I must admit that the technique developed for semilocal Milne K-theory also allows to recover this computation, namely the computation of Motivic complex Z1. And what about Z2? And I'll show that the Motivic complex Z2 is computed on fields as semilocal Milne K-theory. For the other weights, I construct a strongly convergent spectral sequence, which relates all Motivic cohomology sheaves outside the diagonal. As you can see on your screen, the diagonal is highlighted in yellow, and the strongly convergent spectral sequence will relate the semilocal Milne K-theory to semilocal Motivic cohomology. And as you can see on the picture, the diagonal in here is well known, and it was computed by Nesterenko, Suslin, and Bert Tataro, and computed as Milne K-theory of the base fields. But very little is known about cohomology, Motivic cohomology outside the diagonal. And today I'll try to speak something about them. So first of all, Motivic cohomology groups outside the diagonal are known except this group, which is computed as K3 indecomposable of the base fields. I work over any base field K. Next, and I recall that several outstanding conjectures are dedicated to computation of Motivic cohomology, and one of them is the Beilinson-Soulé Vanishing Conjecture, which states that Motivic cohomology in non-positive degrees are all 0. So, and in the charts, you can see the zone of the Beilinson-Soulé conjecture inside the green area, yeah, and outside the green area, the Beilinson-Soulé conjecture says that everything is zero. Next, another conjecture, namely in positive characteristic, the Beilinson conjecture states that the Milnor K-theory and of the base field with rational coefficients coincides with Quilin's K-theory with rational coefficients. And one of the applications of semilocal Milne K-theory will be an equivalent condition to the Beilinson conjecture in positive characteristic. Namely, this conjecture, the Beilinson conjecture, is equivalent to vanishing of the rational semilocal Milne K-theory groups of the base field K as an application of semilocal Milne K-theory. And I recall that there is a computation by Moritz-Kertz for Milne K-theory sheaf. We can compute sections of these sheaves, of such sheaves on semilocal schemes, reasonable semilocal schemes in elementary terms. Okay, and let me start with the definition. I would start with the definition what a rationally constructible presheaf is. So let me pass on to another page, and I would start with the following definition. We consider a presheaf from smooth algebraic varieties over K to abelian groups. And it is called, and we denote by, I follow the notation of Andrei Suslin, paper about Motivic cohomology. At X, we take the co-limit over all U containing X cross 0, 1, and contained in X cross A1, and I take the sections, the section of F at U. And there are two natural morphisms given by restrictions to X cross 0 and X cross 1. Namely, these morphisms are denoted by I upper star 0, I upper star 1, and from C1 tilde F to F. So next we say that F is rationally constructible if there exists if there is a morphism S from F to C1 tilde F, such that the composition of I naught star S equals identity F and I1 star S equals 0. So this is the same definition with constructible presheaf, but this time for C1 tilde F. And let me give a few examples. There are plenty of rationally contractible preshifts. Well, first of all, the naive preshift that's denoted by this symbol. This is a preshift taking a smooth scheme X to home sets in smooth from X to pointed GM. And another reasonable example is if you take finite correspondences and take GM smash N again, or say if you take Calmes-Fazel core tilde correspondences, or for example, if you take linear frame correspondences, for simplicity, I take stable ones, and so on. So these are all rationally contractible preshifts. And in general, I'm dealing with all rationally contractible preshifts with or without transfers. But in practice, for the major applications, of course, my preshifts will all have transfers. But in general, let me start with the following observation. In fact, this is the main observation. Which says that given a chain complex of rationally contractible bounded from above, given a chain complex of consisting of rationally contractible preshifts, we can always associate a strongly convergent spectral sequence to it. But for that, I need a couple of results which are due to Andrei Suslin, and let me recall them. That the following basic properties of rationally contractible preshifts, namely the following conditions are true. The following properties are true. Well, first of all, if I take a rationally contractible preshift, then there is internal home from delta n, algebraic delta n, of course, to F. And second, if F is rationally contractible, then the chain complex F delta hat, I'll explain what delta hat bullet is a bit later, is acyclic. In fact, it is contractible. And as a chain complex of abelian groups, and in particular, it is acyclic. And delta hat here stands for is the semi-localization of the algebraic delta L at its vertices. V0, V1, and Vn. There are n+1 vertices here with coordinates 1, 0, 0, followed by 0, 1, 0, 0, and so forth. And altogether, delta hat L form a cosimplicial scheme, and we evaluate f at delta hat bullets. And a result of Suslin says that this complex f from item 2 of the proposition says that this complex is contractible, and in particular it is acyclic. And I'm now ready to pass on to a theorem which I have already briefly mentioned. Namely, if you consider the following chain complex, a chain complex of rationally contractible pressures. With or without transfers, it does not matter. Rationally contractible say concentrated in the following degrees. Well, I start with f. I'm using cohomological notation on purpose because later I'll be dealing with Motivic complexes, which are co-chain complexes. Therefore, I'm I consider the cohomological notation. And so forth. And the main observation that I can take all cohomology preshifts. Next, I take the following preshifts. First of all, I take kernels, curly k minus a denoted by is the kernel of d minus n, and positive on purpose. And next, and I also take the following preshift. It is the zeroth cohomology of the chain complex, and denoted by L, curly L. So then the chain complex L evaluated at delta hat bullet is quasi-isomorphic to the chain complex K minus 1 evaluated at delta hat bullet and shifted twice. Important. Minus 2 shifts refers to homological shifts here, because I deal with simplicial abelian groups, and they can be identified with chain complexes by Dalt-Kant correspondence, and if chain complexes, then I'm using here homological shift. However, by assumption, I consider the co-chain complexes of complex of rationally contractible pressure. So just to fix notation. So homological shift, but co-chain complex of rationally contractible preshifts. Okay, that's not all. And also there is a tower in the derived category of abelian groups, I recall this is a nice compactly generated triangulated category of the following complexes. Namely, I start with k-1, followed by k-2, delta hat, but shifted -1 homologically. As you can see, the connectedness grows from the right to the left, followed by k-2, k-3, excuse me, delta hat, oops, k-3, delta hat, and so forth. And shifted -2 times. And shifted -2 times. And every such tower with growing connectedness gives rise to a strongly convergent spectral sequence if I use a result of Friedlander and Suslin on Motivic cohomology, on Motivic spectral sequence paper. So such a tower induces, it induces a strongly convergent spectral sequence and I'm going to write plenty of symbols. Namely, it is the spectral sequence as follows. I take the homology group of the following chain complex. I take the -1 -qth cohomology pressure of the complex above, evaluated at delta hat, and take its homology, and it strongly converges to the following: H P plus Q minus 2 plus 2, sorry, of the following complex L, which I introduced above, so let me write the left-hand side also equals HP, homological HP of H minus 1 minus Q of the complex, truncated complex in negative degrees of the cochain complex F bullet, evaluated at delta hat. In other words, this spectral sequence relates negative cohomology pressures evaluated at delta hat to L delta hat. And in practice, if I replace the cochain complex above by, for example, Motivic complex consisting of rationally contractible pressures, I'll arrive at a strongly convergent spectral sequence, and which will lead to some information about Motivic complexes later. So this theorem is more or less the main observation, and it'll be applicable. It'll apply to Motivic chain complexes. So let me pass further down to now to semilocal Milnor K-theory, but before defining it, main application is given for the complex Z mod n, Zn, the Motivic complex of weights n. I recall how it looks like. We take correspondences placed in plus n cohomological degree, next followed by correspondences of delta 1 in cohomological degree n minus 1, and so forth. Say I take correspondences delta 2 and so forth. This is a cochain complex of rationally constructible preshifts by proposition I gave above due to Andrei Suslin. Where is it? Here we are. So given a rationally constructible preshift, internal home from delta n to f is again rationally constructible, as well as, yeah, that's it. And correspondences, finite correspondences evaluated here. It is an example of rationally constructible preshift. And I'll apply this theorem to that cochain complex of rationally constructible preshifts. And similarly, we also can similarly consider the chain complex, similarly Z tilde n for Milnor-Witz Motivic cohomology, in the sense of we take Cortilde correspondences in the sense of Kalmes-Fazel and construct the same cochain complex. So you can easily write it similar as above. Okay, and I'm now defining the semilocal Milnor K-theory. So first of all, the nth semilocal Milnor K-theory complex denoted by say curly K upper M for Milnor and for the weights, and I take delta hat of the base field K small. This is a chain complex, and where I recall that is where curly K is the sheaf, Milnor sheaf, Zariski sheaf. Yeah, it is the nth cohomology preshift of the complex above here. So I take this complex and I take cohomology in this degree, and by definition, this and by a theorem of Moritz-Kertz, it is the sheaf of we can compute it explicitly, especially on semilocal schemes, if the base field is infinite, by the way. Okay, but formally, I take the nth cohomology sheaf of that complex and then evaluate it at delta hat. And by definition, this is the nth semilocal Milnor K-theory complex. And similarly for the Milne width, I define the Milne width complex. I take again the nth cohomology pressure of core tilde complex in the complex Z tilde n, and take its cohomology in the nth degree, and evaluate it again at delta hat. And the homology groups and the NQ semilocal Milne K-theory or Milne width K-theory is the following abelian group. I denoted it by K and Q, hats of the base fields K, and by definition, it is the qth homology of the Milne chain complex delta hat. And by definition, the semilocal Milne K-theory consists of, it is a bigraded abelian group, and basic properties that semilocal Milne K-theory groups are, for example, invariants under purely transcendental field extensions. This is an important property for semilocal Milne K-theory, and which is not true for other versions of Milne K-theory. Also, another property, if the base field is of positive characteristic, characteristic P, then semilocal Milne K-theory is P uniquely divisible. Also, I recall that Milne, the usual Milne K-theory of fields is P torsion-free, but semilocal Milne K-theory is moreover, it is P uniquely divisible. And the latter property follows from the theorem of Geisser and Levin about Motivic complexes with Z mod P coefficients. So these are two important properties for semilocal Milne K-theory groups. And here's the main theorem for semilocal Milne K-theory, namely the following statements are true. First of all, there is no semilocal Milne K-theory for Q equals 0 or 1. So for n larger or equal than 1, Kn 0 of K equals semilocal Milne. So for Q equals 0 or 1, there is no semilocal Milne K-theory, and K00 of K, of K equals Z. Another property, I apply the strongly convergent spectral sequence above to say that there is a strongly convergent spectral sequence starting at pith homology of, if I take -1, I should shift n -1 minus q, Zariski, evaluated that I take the truncation minus n of the Motivic complex Zn, evaluated at delta hat k, it converges to semilocal Milne K-theory, and p plus q plus 2. In other words, this spectral sequence relates semilocal Milne K-theory to Motivic cohomology in each weight concentrated exactly outside the diagonal. Exactly. Next, if in weight 2, the spectral sequence collapses, and there are isomorphisms as follows. I take the pith cohomology evaluated at K of the complex Z2, Motivic complex of weight 2. And this is nothing but the semilocal Milne K-theory group 2, 3, minus P. Using my indexing and notation. So as we can see, for P less or equal than 1. In particular, K3 indecomposable of the fields is recovered as semilocal Milne K group with indices 2 and 2. So the Motivic complex of weight 2 is fully recovered by semilocal Milne K-theory groups. And fourth, basing on Tom Bachmann's computations for Milne-Witt cohomology, we can conclude that there are natural isomorphisms namely from Milne-Witt semilocal groups to Milne semilocal. So this is a natural morphism of abelian groups, and it turns out that this is an isomorphism for all Q and n larger or equal to 1. So in other words, delta hat annihilates or deletes the information about quadratic forms, and what it leaves the semilocal Milne K-theory. And this computation is based on Bachmann's results for Milne-Witz Motivic cohomology. Next, I don't have lots of time, but I would mention a couple of properties, namely, let me mention the following property. If I take X in smooth K, K is perfect, then HP evaluated at X and with coefficients in Z2 is computed as Milne K-theory with coefficients 2, 3 minus P of the function field of X. And I assume that X is connected. Next property, another property, is that for any n larger or equal than 3, the groups K2 with coefficients 2n Milne is uniquely divisible. Also, another property says that there are isomorphisms as follows: K3 of K, K3 of K with rational coefficients, and as I mentioned above, Milne with rational coefficients. Also, K 4 plus P, 4 plus P of K with rational coefficients as Milne K-theory groups with rational coefficients. And P is larger or equal than 0. Also, the above theorem implies that K3 of K is fully determined by Milne K-theory of the field and semilocal Milne K-theory groups with coefficients 2 and 2. Next, and the technique which is developed above allows to formulate several criteria for the Beilinson-Soulé conjecture. So let me pass to the Beilinson-Soulé conjecture. Says that each Motivic complex Zn is concentrated in cohomological degrees from 1 to n. And outside this interval, the BS conjecture states that Motivic cohomology groups are 0. Well, the following theorem is true. The BS conjecture can be reduced to to the following computation. Instead of verifying that the Motivic complex in weight n is zero outside for in non-positive cohomological degrees, we can associate a chain complex of abelian groups, and it is enough to verify that every such complex is acyclic of abelian groups. So the following, namely the following statements are equivalent. Namely, the BS conjecture is true for Motivic complexes Zn. Second, let me take the following sheaf. I take kernel of d naught, where d naught is the differential, zeroth differential of Motivic complex Zn. Then, d naught, where d naught is the zeroth differential of the complex Zn. Then the BS conjecture is equivalent to the following. If I take this Zariski sheaf and evaluate it at delta hat, where it is required to be, it is acyclic for all finitely generated field extension, K capital of the base field K small. Also, the BS conjecture is equivalent to the following. Every chain complex of abelian groups namely, I take the truncation in degrees between 1 and n of the complex Zn, and I evaluate it at delta hat. This is a chain complex of abelian groups, and it is acyclic. And also, I can similarly write every chain complex. If I truncate the chain complex Zn and take so less or equal than 0 of the chain complex Zn, evaluated at delta hat, is acyclic. So most importantly is property 2, which states that if I take a particular sheaf, the Zariski sheaf, namely I take the kernel of the differential d naught or in the complex Zn and evaluate this Zariski sheaf at delta hat, and if it is acyclic for every n, then the BS conjecture is true. Another application of the technique is for K-theory for K4 of the field. I recall that by results of Levin, Merkurov, and Suslin, we have a description of this group K3 indecomposable, where K3 indecomposable fits into the short exact sequence of abelian groups. And there are plenty of descriptions of K3 indecomposable. And as I mentioned earlier, we recover this K3 indecomposable as semilocal Milne K-theory group K hat 2. So in other words, K3 of the fields is fully determined by Milne K-theory of the base field and semilocal Milne K-theory. And similarly for K4 of the field, namely it is completely determined by Milne K-theory and associated semilocal Milne K-theory groups. I don't have time to give details about Motivic spectral sequence and how I arrive at this at the following theorem. I only have time to formulate it, I'm afraid. So namely, if K is any field, then the following statements are true. First of all, K4 of the base field K is entirely expressed in terms of Milne K-theory and semilocal Milne K-theory. So namely, we have a bunch of exact sequences. I start with semilocal Milne K group with indices 2 and 4. Then I go to, I map it to an abelian group A. I'll then fit A into another short exact sequence, followed by K4 of the field K and epimorphism to semilocal K-theory with indices 2 and 3, where A fits into exact sequence of the Milne K-theory and another abelian group B, where B fits into exact sequence. I take a direct sum, the direct sum of semilocal Milne K-theory, and take residue fields at all closed points outside 0 and 1. X is closed. And then map it to B, and then map it to semilocal K32 of K. This is the general case. If I take rational coefficients, then I have the following isomorphism. K4 of the fields with rational coefficients. There is an isomorphism, Milne K4 of K, O plus, semilocal Milne K32 with rational coefficients, O plus, semilocal K23, which is uniquely divisible, therefore So it is with rational coefficients already, O plus F, where F is a direct summand of the following direct sum of semilocal Milne K-theories groups. I take semilocal Milne K-theory to 2 of the residue field Kx with rational coefficients. And finally, if K is algebraically closed, then there is an isomorphism K4 of K is isomorphic to Milne K4 O plus semilocal Milne with rational coefficients, O plus K23, and O plus the same abelian group F as above. And I've got more 3 minutes, and I'd like to finish with another application of semilocal Milne K-theory groups, namely, let me give a criterion for the Beilinson conjecture, which I formulated at the beginning of the talk. Namely, I recall that it says that Milne K-theory and Quillen's K-theory of K agree rationally whenever K is of positive characteristic. So let me finish with the following theorem, namely the Beilinson conjecture for rational algebraic K-theory for rational algebraic K-theory of fields of positive characteristic is true if and only if rational semilocal Milne K-theory groups vanish, if and only if the semilocal Milne K-theory with rational coefficients namely are all 0 for all m integer and n larger or equal than 1. Okay, and this is essentially everything I was going to tell about, and many thanks for attending my talk. Thank you.
Yeah, Grigory, thank you very much for your talk. Let's thank Grigory at first. Thank you. Yeah, then are there any questions or remarks? Yeah. I don't know. Okay. This seems to be, at least at the moment, we can maybe in the chat afterwards ask more questions or ask questions.
I have a question.
Okay, yes.
Do you have more computation of the semilocal Milne K-theory? Just not only by vanishing results, but just something more doable.
What do you mean by more doable?
I mean, just give more example of computations. Just.
Yeah. First of all, for example, Milnor K-theory groups, due to a theorem of Moritz-Kertz over infinite fields, can be defined in elementary terms, in terms of generators and relations, and I mean semilocal Milnor K-theory complexes, and we take homology. So first, and for example, another property, important property, is that which I consider as a particular computation, is that semilocal Milnor K-theory is invariant under purely transcendental field extensions.
Okay.
And this is, I hope this property will be very useful in further computations around the conjectures I am speaking about today.
Yeah. Okay.
But at the moment, of course, I have mentioned everything I've got at the moment. But my primary goal, as I told at the beginning of the talk, is the computation of Motivic complex Z2. Yeah, for example. And to reduce the BS conjecture to hopefully to some simple objects, and instead of verifying that Motivic complexes are acyclic in non-positive degrees, we need to verify that associated simple complexes of abelian groups are acyclic. Yeah. And yeah, that's all for the moment.
Okay, thanks.
Okay, thank you. Are there more questions, maybe?
Maybe a comment. I think that most of the notation in the beginning part of his lecture was in the Block-Otto conjecture paper of Suslin and Voevodsky that appeared in the Bond proceedings. Am I correct, Grigory?
As you may have observed, Chuck, I have not mentioned any semilocal Milnor K-theory with finite coefficients, which is perfectly studied. So I only deal with integer coefficients, and in fact, more interesting with rational coefficients. Some of the properties, for example, P unique, that semilocal Milnor K-theory groups are uniquely P divisible, are based on heavy theorems by Geisser, Suslin, by Geisser, Levin, and also other properties that some semilocal Milnor K-theory groups are uniquely divisible. This is also a consequence of Bloch-Kato conjecture, of course. And
okay.
At these places, Chuck, by the way, I refer to your book where these properties are mentioned, that some Motivic cohomology groups must be uniquely divisible.
Thank you.
Jo, do we have more questions? Okay, then this seems not to be the case. Then before we thank Grigory again, I would like to announce the Motivic Geometry Conference, which will take place next week, also online. So I think you can use the same Zoom link. So yeah, please consider to take part in this conference. Okay, then I think we thank Grigory again. Thank you very much. Okay. Yeah, I think then we can, the official part is now ended of the